This video will cover how to set up the lock-in configuration for the third generation of basic fiber photometry systems driven with a fiber photometry console. Before diving into the software, we will quickly run over required background information. To skip this section, jump to the timestamp below. The fluorophores for fiber photometry have specific excitation and fluorescent wavelengths which are important to know when setting up the lock-in configuration. Some fluorophores, such as GCamp, have an excitation wavelength that emits calcium-independent fluorescence. This wavelength is called the isobestic excitation and is commonly used to control for motion artifacts. Before setting up the lock-in, it is important to understand how the system is connected. In this example, a fiber photometry console is used to drive two Gen.3 minicubes connected to an assisted fiber optic rotary joint. This system will record a green and red calcium indicator, GCamp and RCamp, from two different sites in a freely moving animal. Let's take a closer look at the fiber photometry console. There are three analog outputs, each of which branch to control the same LED on both minicube. Analog out 1 connects the IE ports and control the isobestic excitations. Analog out 2 connects to E1 ports and control the GCamp calcium-dependent excitations. And analog out 3 connects to E2 ports and controls the RCamp excitations. The console also receives 4 analog inputs. Analog in 1 and analog in 3 are the combined isobestic and calcium-dependent GCamp signals from the F1 ports of each minicube and will be demodulated within the software. Analog in 2 and analog in 4 receive the RCamp signals from the F2 port of each minicube. After understanding the system, we can open Doric Neuroscience Studio to configure the fiber photometry console software interface. Since the LED driver is embedded within the Gen.3 minicubes, there is no need to configure the LED driver within the software. To set up the lock-in configuration in the acquisition console interface, select Add Channel, then choose Analog In on the left panel. The channel name here corresponds to the input of the same number on the console. Since the example system today has 4 inputs, we will create 4 separate channel configurations. For the mode, specify lock-in. The saturation here depends on the type of detector, which for all integrated minicubes is the Doric detector. Each column and the lock-in options below corresponds to the analog output channel of the console. For analog input channel 1, the isobestic point and the GCamp fluorescence are combined, so both analog output channels that drive their excitation should be enabled. Here, the trace name represents the analog in number and the analog out number of the lock-in channel. We will be able to rename this channel later on. Below are the sinusoidal frequencies that modulate the LED intensity. Each LED has a specific modulation frequency that is required to demodulate multiple signals from one input. We strongly recommend using the default frequency options as they have been optimized for fiber photometry. For the LED maximum current, we recommend using the FMC Gen.3 mode because it provides sufficient power for most fiber photometry experiments while permitting a larger dynamic range and more stable recordings. In this mode, 1 volt corresponds to 100 microamperes of current. The LED power must be determined by the user since the value will depend on several external factors. Measure individually the power of each LED one at a time at the tip of the fiber with a power meter. Change the percentage according to experimental needs. This range is typically between 10 to 100 microwatts. To reduce photo bleaching, we also recommend that the LED power of the isobestic excitation be half or less of the calcium-dependent signal. You can always come back later to edit these values. The values of Vmax and Vmin are automatically set based on the LED power and LED maximum current. Lastly, the low pass frequency value determines the bandwidth of the demodulated signal. The default value is 12 Hz and should be adequate for most fiber photometry experiments. Select Add to create the first analog input and its corresponding output channels. The current configuration with one analog input channel would work for a simple system recording GCamp at a single site. To add the RCamp input at the same site, select Analog N2, the lock-in mode, and the Doric detector. Since the RCamp signal only requires a 560 nanometer yellow excitation, we will only enable channel 3. Again, the output power setting should be measured and set individually. Select the Add button to create the second input channel. This two-input channel configuration would work for a system recording GCamp and RCamp at one site. Adding a second minikube for a second site is similar to what we've already done. Analog N3 will be the GCamp signals, so we can enable the first two channels since they are driven by the same analog out as minikube 1. And then for analog N4, enable only analog out 3 once more. Here, we've finished the lock-in configuration with 4 input channels for a GCamp and RCamp recording at 2 different sites. In the acquisition view of the Fiber Photometry console interface, we can see all 4 analog input channels that were created. Here, each input has its own window, and we can find the corresponding outputs within these tabs. Click Edit to change the LED power or other parameters. Select Graph to modify the trace names. Here, we can specify the raw signal, the isobestic signal, and the calcium-dependent signal. We can also change the colors of the trace to make them more intuitive. We can even hide a trace by selecting the empty slot from the drop-down menu. When we close the graph window, we can see that the name and color changes have been made on the graph. You can organize the view by sliding the different channel windows around. Here, we organize the graph window so that all 4 analog inputs could be simultaneously viewed, with minikube A at the top and minikube B below. To save this configuration, including parameters, visualization detail, and window displays, select Save Configuration. If we clear the window, we can quickly re-import the settings using the Load Configuration button. To specify where the data will be saved, click Saving Options. Here, we can specify the file name where the data will be saved. Note that for version 6 of the software, the data can only be saved as an HDF5-based .doric format. On our website, we provide MATLAB, Python, and Octave codes to easily read this file format. To reduce the file size, you can also specify the decimation factor, which by default is 200x when in the lock-in mode. This means that only one data point is saved for every 200 data points collected. To begin an acquisition, select either Live mode to quickly check the signal, or Record mode to save the data. Let's do a dry run to test the acquisition system. When optic fiber B is touched, the amplitude of the raw signal in blue and the demodulated traces in purple, green, and red fluctuate only on the channels corresponding to minikube B. When touching the fiber in ambient light, the amplitude of the raw traces diminishes because the total amount of light collected is reduced, whereas the amplitude of the demodulated traces increase since they are only picking up the endogenous fluorescence emitted by the skin. The system is now ready to be used with a test animal for experiment-specific optimizations. If you require further technical support, please reach out to us at support@doriclenses.com.